We move through the world with a quiet, unspoken certainty that reality exists whether we pay attention to it or not. A mountain does not vanish when no one is looking. The moon continues its orbit while we sleep. The universe we assume is there, solid, objective, and independent of our presence. This belief feels so obvious that questioning it seems almost absurd. After all, reality is supposed to be the one thing we don't have to worry about. For centuries, both philosophy and science were built on this assumption. The universe was treated as a stage, and we were merely observers walking across it. Events happened whether or not anyone was there to witness them. Observation revealed reality, but it did not create it. This idea was not just comforting, it was practical. It allowed scientists to describe nature as something external, measurable, and unaffected by human perception. But in the early 20th century, this picture began to fracture as physicists pushed deeper into the smallest scales of nature, far beyond atoms, into the realm of subatomic particles. They encountered behavior that refused to fit common sense. At this level, particles did not behave like tiny solid objects moving along predictable paths. Instead, they behaved like possibilities. They spread out, interfered with themselves, and existed in multiple states at once. Most unsettling of all, their behavior seemed to depend on whether or not they were being observed. This led to a question that still has no agreed upon answered. What if reality, at its most fundamental level, does not exist in a definite state until it is observed? At first, this idea sounds like a misunderstanding, or perhaps a poetic exaggeration. Surely the universe does not wait for human eyes to decide what is real. Surely particles do not care whether we are watching them. And yet, the mathematics of quantum physics, the most accurate theory ever devised, suggests exactly that. It does not describe particles as having definite properties at all times. Instead, it describes probabilities that only resolve into specific outcomes when a measurement occurs. This is not a philosophical trick. It is not science fiction. Quantum theory works with astonishing precision. It predicts experimental results to an accuracy unmatched by any other scientific framework. And yet, the theory itself seems to say something deeply disturbing. Before observation, physical systems exist in a kind of undefined state, not here or there, not this or that, but all possibilities at once. This is where the discomfort begins. If observation plays a role in determining outcomes, then what does that say about reality itself? Is the universe fundamentally incomplete without measurement? Is reality something that unfolds independently, or something that only becomes definite through interaction? And if observation matters, what qualifies as an observer? A human? A measuring device? Any interaction at all? Scientists care about these questions not because they undermine everyday experience, but because they strike at the foundation of physics. Quantum mechanics does not merely challenge how we describe reality, it challenges what reality is. It forces us to confront the possibility that the universe is not a collection of fixed objects, but a web of potentialities that only crystallize under certain conditions. The stakes are enormous. If reality is not fully real until it is observed, then objectivity itself becomes questionable. The boundary between observer and observed begins to blur. The universe is no longer a passive system unfolding on its own, but something that responds to interaction in fundamental ways. This does not mean the world disappears when we look away, but it does suggest that beneath the solid surface of everyday experience lies a deeper layer where certainty does not exist until it is forced into being. And that leads us to the central mystery of quantum physics, a mystery that has divided scientists for more than a century. Before quantum physics unsettled everything, reality seemed simple in the best possible way. The universe was governed by clear rules, predictable laws, and a comforting sense of order. Objects had definite positions. Time moved forward at a steady pace. Causes led to effects. And most importantly, things existed whether or not anyone was watching. This picture of reality did not just feel intuitive, it worked. It allowed humanity to build machines, predict planetary motion, and send spacecraft across billions of kilometers of space. This worldview reached its most complete form in classical physics, shaped by thinkers like Isaac Newton. In this framework, the universe behaved like an enormous clockwork machine. Every particle had a precise position and velocity. If you knew the current state of the system well enough, you could, in principle, predict its entire future. Uncertainty was not built into nature itself. It was merely a limitation of human knowledge. Reality, at its core, was deterministic and fully defined. Even when physics evolved beyond Newton, the basic assumption remained intact. Einstein's theories of relativity transformed our understanding of space and time, showing that they could bend, stretch, and slow down. But relativity never suggested that reality depended on observation. Events still happened objectively. The universe did not need an audience. Light traveled whether or not anyone saw it. Stars burned regardless of human awareness. Reality remained real on its own terms. This is how we learn to think about measurement. A measurement was simply a way of revealing information that was already there. When you measured the temperature of a room, you were not creating the temperature, you were discovering it. When astronomers measured the position of a planet, they assumed that planet already occupied that position before the measurement. Observation was passive, not creative. This mindset extended naturally to how we imagine particles. Even when scientists accepted that atoms existed, they still pictured them as tiny objects with definite properties. An electron, in this view, always had a position, a speed, and a path, even if we didn't know exactly what they were. Probability was a tool for managing ignorance, not a statement about reality itself. This classical intuition felt unshakable because it matched everyday experience. A ball thrown through the air follows a smooth trajectory. A chair remains in place when no one is looking. The world behaves consistently and predictably on human scales. And for a long time, there was no reason to think that deeper layers of reality would behave differently. But cracks slowly began to appear. As scientists studied light and matter more closely, certain experiments produced results that refused to fit classical explanations. Light sometimes behaved like a wave, spreading out and interfering with itself. Other times, it behaved like a particle, delivering energy in discrete packets. Matter, too, displayed wave-like properties under certain conditions. These behaviors were not just strange, they were incompatible with the idea that objects always had well-defined properties. Classical physics had no place for such ambiguity. A thing was either here or there, moving or not moving, a wave or a particle. The idea that something could exist in multiple states at once was not merely counterintuitive, it was forbidden. Yet nature did not seem to care what felt reasonable. The old framework still worked beautifully for large objects and everyday phenomena, but it began to fail at the smallest scales. And with each experimental anomaly, it became harder to believe that reality was as simple and observer-independent as we had assumed. The universe was about to reveal that our most trusted picture of reality was not wrong, but incomplete. The moment reality truly began to unravel did not come from philosophy or speculation. It came from experiments, quiet, carefully controlled experiments that produced results no one wanted, but no one could ignore. As physicists pushed deeper into the microscopic world, they discovered something profoundly unsettling. Particles did not behave as if they possessed definite properties until they were measured. And worse, the act of measurement itself seemed to change what reality was doing. One of the earliest cracks appeared in the famous double-slit experiment, when particles like electrons were fired one by one at a screen with two narrow slits. Scientists expected a simple result. If electrons were particles, they should pass through one slit or the other, creating two clusters on the detection screen. But that is not what happened. Instead, the electrons formed an interference pattern, a hallmark of waves. Each individual particle appeared to behave as if it passed through both slits at once, interfering with itself. At first, this was strange but manageable. Physicists assumed that the electron was still a particle. It was simply guided by a wave, like mathematical description. But then the experiment took a more disturbing turn. When scientists placed detectors at the slits to observe which slit the electron passed through, the interference pattern vanished. The electron suddenly behaved like a particle again, choosing one slit and one path. Nothing else in the experiment changed. The only difference was observation. This result was not subtle. It was repeatable, measurable, and undeniable. When no one watched, particles behaved like waves spread out, undefined, existing in multiple possibilities at once. When observed, those possibilities collapsed into a single outcome. Reality itself appeared to respond to being looked at. Physicists tried to avoid the implication. Maybe the measuring device disturbed the particle physically. Maybe the interaction caused the change. But increasingly refined experiments showed that it was not just disturbance, it was information. The moment the system became measurable in principle, even if no human checked the data, the behavior changed. Reality seemed to care not about consciousness, but about observation as a process. This forced scientists to introduce a concept that had no place in classical physics superposition. Before measurement, a particle did not exist in one state or another. It existed in a combination of all possible states at once. Not metaphorically, not mathematically only. Experimentally, even more unsettling was the role of probability. Quantum mechanics did not predict exact outcomes, only probabilities. And these probabilities were not about ignorance. They were fundamental. The theory did not describe what is, but what might be, until measurement forced a decision. Albert Einstein famously rejected this idea. God does not play dice, he argued. He believed there must be hidden variables, unseen properties that determined outcomes behind the scenes. But decades of increasingly precise experiments, including tests of Bell's inequalities, ruled out local hidden variable explanations. Reality could not be both local and predetermined in the way Einstein hoped. What remained was deeply uncomfortable. According to the best tested theory in science, the universe does not fully exist in a definite state until interactions occur that count as measurements. Before that, reality is described not by facts but by possibilities. Importantly, physicists were not claiming that human consciousness magically creates the universe. That interpretation remains controversial, but what they could not escape was this observation is not passive. It is participatory. The act of measuring does not merely reveal reality, it helps define it. This was not mysticism. It was mathematics backed by experiment, and it raised a question that physics had never needed to ask before. If reality needs observation to become real, then what exactly is reality when no one is looking? Once physicists accepted that observation plays a role in shaping outcomes, the next question became unavoidable: how does this happen? Quantum theory gives incredibly accurate predictions, but it refuses to explain what is actually going on underneath. To this day, scientists are divided into competing interpretations, not because they enjoy disagreement, but because the data allows multiple, deeply strange explanations. Each one works mathematically. Each one feels disturbing in a different way. One possibility is the Copenhagen interpretation, the oldest and still one of the most widely taught views. According to this idea, quantum systems do not possess definite properties before measurement. Reality exists only as a wave of probabilities, and measurement causes the wave function to collapse into a single outcome. In this view, asking what a particle really is before observation is meaningless. There is no underlying reality to describe. This interpretation works remarkably well, but it leaves a haunting gap. It never explains why measurement causes collapse or what counts as a measurement in the first place. Is it a detector, an interaction, information, or something deeper that we still don't understand? Another possibility is the many worlds interpretation, which removes collapse entirely, but at a shocking cost. In this view, the wave function never collapses. Instead, every possible outcome of every quantum event actually happens. The universe constantly splits into countless branches, each representing a different version of reality. When you observe a particle, you don't force it into one state. You simply find yourself in the branch where that outcome occurred. This interpretation preserves mathematical consistency and avoids special rules for measurement. but it implies an unimaginable number of parallel universes. Reality becomes an ever-expanding tree of possibilities, most of which we can never access or observe. A third idea is quantum decoherence, which sounds less dramatic but hides profound implications. Decoherence suggests that quantum systems interact with their environment so rapidly that superpositions become effectively unobservable. The system doesn't collapse in a fundamental sense, it simply becomes entangled with everything around it. Classical reality emerges because quantum coherence is lost to the environment. This explanation helps bridge the gap between quantum and classical worlds, but it does not solve the core mystery. Decoherence explains how things appear classical, but not why one outcome is experienced instead of all others. Then there is relational quantum mechanics, which proposes something even more unsettling, that reality itself is relative. In this view, physical properties do not exist absolutely, they exist only in relation to other systems. A particle can have different properties depending on what is observing it. There is no view from nowhere, no universal description of reality. Every interaction creates its own version of truth. This interpretation challenges the idea that the universe has a single, objective state shared by all observers. Some physicists explore information-based interpretations where information, not matter or energy, is the most fundamental ingredient of reality. In these models, physical properties emerge from informational relationships. Measurement is not about revealing reality, but about updating information. The universe behaves less like a machine and more like a vast computational process. While intriguing, these ideas raise uncomfortable questions about whether reality exists independently of information processing at all. Finally, there are more speculative ideas that push the boundary between physics and philosophy. Some researchers ask whether space-time itself is emergent, not fundamental, but arising from deeper quantum relationships. In such models, the familiar world of space and time only comes into existence through interactions. Without observation, like processes, reality may not even have structure. What makes these possibilities disturbing is not that one of them is clearly true, it's that no experiment so far has ruled most of them out. Quantum mechanics works perfectly, but its meaning remains open. Each interpretation forces us to give up something we instinctively believe: objective reality, uniqueness of the universe, independence of observation, or the idea that the world exists fully formed whether we look or not. Scientists are not hiding answers. They simply do not have them. And perhaps the most unsettling possibility of all is this: the question may not be which interpretation is correct, but why does reality allow so many incompatible explanations to work? At the deepest level, physics may be telling us something we are not comfortable hearing, that reality is not built the way human intuition expects. If quantum physics is telling us that reality does not fully exist until interactions occur, then the implications stretch far beyond laboratories and equations. This is not just a technical problem for physicists, it quietly reshapes how we understand existence itself. The universe begins to look less like a solid structure and more like an unfolding process, where certainty emerges only through interaction. For centuries, humanity assumed the universe was complete and indifferent. Stars burned, planets moved, and time flowed the same way whether anyone was watching or not. Quantum mechanics does not directly deny this picture, but it weakens its foundation. At the deepest level we can currently probe, reality seems less definite, more conditional. What we experience as a stable world may be the result of countless interactions, continuously reinforcing one outcome over others. This does not mean the universe depends on human consciousness in any mystical sense. Most physicists reject that idea, but it does suggest that relationships matter more than objects. Reality may not be made of things with fixed properties, but of interactions that give rise to properties. Existence becomes relational, not absolute. That shift carries philosophical weight. If properties only become real through interaction, then asking what the universe is really like in isolation may be the wrong question. The more accurate question may be how different parts of the universe relate to one another and how those relationships create the world we experience. There is also a humbling lesson here. Humans are not the center of this process. Measurement happens everywhere particles collide, fields interact, information spreads. Reality is constantly being shaped without us. We are participants, not authors. Observers, but not privileged ones. The universe does not wait for human attention. It evolves through interaction at every scale. At the same time, this perspective changes how we think about knowledge. Science no longer looks like a simple uncovering of pre-existing truths. Instead, it becomes a dialogue between observer and system. We design experiments, ask questions, and the universe answers, but not always in the way we expect. Each answer opens deeper uncertainty, revealing not ignorance, but structure beneath appearances. This uncertainty is not a failure of science. It is evidence of its honesty. Quantum physics does not pretend to offer comfort. It offers precision where possible and silence where understanding ends. That restraint is what makes it powerful. Perhaps the most profound implication is this reality may not be there, in the way we intuitively imagine. It may be more like a story that only gains detail as it is told, a universe that becomes more specific through interaction, not one that was fully written from the beginning. And yet, this does not make existence meaningless. If anything, it makes it richer. A reality that emerges through interaction is dynamic, not static. It invites participation, not passivity. Meaning is not diminished, it is created continuously, through relationships, observation, and inquiry. In the end, quantum physics does not tell us that reality is an illusion. It tells us that reality is deeper, stranger, and less intuitive than our everyday experience suggests. It reminds us that certainty is rare, questions are fundamental, and understanding is always provisional. The universe did not give us final answers. It gave us better questions.